So today, from PLAXIS, that is Bentley, joined Dr. William. He is the principal consultant for PLAXIS for Geotechnical Division, and Dr. Rajendra, Bisht, he is Geotechnical Division. He finished his research in IIT Bombay. So today he is going to give beautiful that modeling for some techniques in sealed tunnel. So we will take a notes for how to do in PLAXIS. He will explain more about modeling techniques in shielding tunnel. Okay, let's see. We invite to Dr. Rajendra to take care of further session.
Thank you for the kind introduction. Good evening, everyone, and welcome. Today's webinar is on the topic practical modeling techniques in shield tunneling. The webinar provides an introduction on the topic modeling, modeling and tunneling using PLAXIS CE. And the main focus will be on numerical simulation of the shield supporting tunnel. For those who are interested, a comprehensive webinar on this topic is also available and can be found on the Bentley on demand webinar. First, this is the outline of my presentation. I'll start with a brief introduction about tunneling using the TBM, and then I'll move to the part one of the presentation where I'll speak about the operational feature that is Tunnel Designer in PLAXIS 2D and 3D. After that, I'll discuss about simulation of tunneling sequence, followed by what are the direct inputs and result we get from the PLAXIS analysis. I'll start the first part of the presentation. Now the development of the infrastructure is increasing in urban areas in almost all the countries because of the growth of population and also economy. So in urban areas, the tunneling activities is increasing to improve the road and railway connectivity, or to adapt the MRTs, or to expand water supply, or to improvement the public utility services. So the left hand top figure is showing the MRT tunnel, and the bottom one is showing you the utility tunnel that were constructed using the TBM method. And the right hand side, you can see the road tunnel and railway tunnel that were constructed using the NATM, New Australian Tunneling Method. So for today's presentation or webinar, so for today's webinar, I'll be mainly focusing on the left hand side figures where the tunnel were constructed using the TBM method. So there are different tunneling methods such as cut and cover method, drill and blast method, or you have a TBM, which is a tunnel boring machine, which are of different type. Either you can have a earth pressure balance machine or a slurry type of machine. That's mainly to support your face of the tunnel during the tunnel construction. Or you can use the NATM method, New Australian Tunneling Method, for the tunnel construction. The approach to which method to adopt or choose depends on many factors, such as the geological condition, space constraint, location, and cost allocation to the project. But tunneling in urban areas can be quite challenging. First, because of the space constraint, and second, if the existing infrastructures or structure is sensitive to the ground movement, so that could create a lot of problem during the tunneling process. So in urban areas, excavation using TBM can be more effective to reduce the disturbance and also ground movement. Now here on your left, you can see a picture of TBM and its components. So a TBM is a large, advanced, sophisticated machine that is used for tunnel excavation, and it consists of a rotating cutting wheel. The diameter of this cutter head or a rotating cutting wheel can varies from a few meters, and the largest one was used was the 17.4 meter in China. So you can you can assume how big are these machines are. So the main part of the tunnel boring machine, the cutter head, or the rotating cutting wheel, excavate the material from the tunnel face, and the excavated material is then transferred to the rear of the TBM using the conveyor screw. That is number 6 on your as shown in the figure, left hand side figure. Then the prefabricated reinforced concrete segments are used to form tunnel lining, and these segments are bolted together to form the tunnel cross section mainly. And then by using the hydraulic or a thrust cylinder or hydraulic jack, the hydraulic jack pushes itself against the newly installed lining, and then the tunnel boring machine move forwards and drill further. So the main advantage of this tunnel boring machine is it produces low vibration, and it reduces surface and ground disturbance compared to your other drill and blast method. Or it is also a very faster way of excavation, and it doesn't produce any harmful gases or noise pollution. So it's more environmental friendly. So now the tunneling using TBM consists of many stages and many stages or mechanism, and also excavation cycles. So tunneling process using TBM can be simulated numerically by using pressure or contraction, and by using the boundary condition at the tunnel front, middle, and at the tail. But researchers and numerical modeler have developed 3D finite element models that take into account all relevant component of a tunnel construction process, such as the phase pressure, tunnel TBM conicity, grout pressure, installation of your lining, and jack forces, etc. So hence in the figure you can see that we have 6 different TBM and 3D models, uh, and however, for a practical purpose, one may only focus on the most important factor or of the excavation, or most important aspect of the construction tunnel boring process. So, depending on the experience and expertise in the numerical model, one may choose uh, different tunneling 3D models. So, the TBM and 3D is corresponding to the PLAXIS tutorial. So, you can see that here we have a phase pressure, and for tunnel conicity we have a contraction, and then grout pressure. But few who advanced or few very accurate or popular models are Moller's model and Loganathan model. So in Moller model, the Moller use only model the gap between the tunnel lining and the excavated surface, and use the grout pressure for deformation. Similarly, Loganathan only considered three losses, one at the face due to the face pressure, and one at the middle, or a shield loss due to the gap between the tunnel shield and the excavated surface, and third, at the tail loss due to the gap between the grout and the excavated phase. So using a very simple model also you can completely get the correct result as well. Now so in addition to modeling of a geometry correctly, one should also take care while choosing the correct material model for the analysis of any geotechnical problem. So Plaxis have a extensive soil model library for modeling of clay, sand, and rock. And also in Plaxis, we do have two sets of model that are standard soil model and a user-defined soil model that can be used for modeling of any particular type of problems. Apart from the modeling, soil is a continuum element. We also need a structural element. So we also have a different type of structural element, such as a beam element or plate element. Uh, so plate elements are mainly will be very useful in modeling of the shield of that TBM in the tunneling process, and other structural element as well. Now, moving to the first part of the presentation, now here we will see how we can use the uh, special operational feature in Plaxis 2D and 3D, that is Tunnel Designer, for the modeling of the tunnel, shield tunnels. So, TBM method can be used for different soil conditions and location. There are key TBM engineering issues, such as the first one is the settlement or the ground movement. So ground movement should not be excessive during the projected life of the tunneling during the project life of the tunnel. And second, the lining forces segment must withstand the overburden pressure that is coming from the top of the soil. And then we have a tunnel face stability, which we need which we need to consider to avoid any type of the collapse. And the fourth is the impact of the tunnel lining process, and the impact should be minimum. And Those who are further interested to explore more about the tunnel or foundation interaction, they can refer to the Bentley latest on-demand webinar. There is a Bentley webinar on modeling of tunnel and tunneling using TBM. Now, next we have a uh, first we have a now simple tunnel designer in 2D. So here we have a simple case uh, of a tunnel cross section of 6 meter diameter, and here 0.2 meter thick tunnel lining, and the crown of the tunnel is located at a depth of 2 times the diameter of the tunnel. So what here we have a simple case of a circular safe tunnel, but tunnel designer can be used to model different tunnel cross section or complicated tunnel cross section as well. And Plexis also allow the user to import different type of shape for the tunnel, different type of shapes for the tunnel construction. So you can import different cross section, tunnel cross section using the tunnel designer. Next, we will have a short video clip to show how the tunnel designer can be used to model a circular tunnel in 2D. So, so we will start the our tunneling construction by first by the naming, and then we have two different type of models, the plane strain model or axis symmetry model. Since we are dealing with a tunnel here, so we can choose the plane strain model. And here we are defining the our dimension of our soil model here. And once that's done, now here in Plexus we have 5 different modes, or that's our soil mode and structure mode, or a flow condition mode, mesh mode, and a stage construction mode. So in soil mode, first the soil stratigraphy is defined using the create borehole option, and you can add different layers, different soil layers by using the add button, and you can define also define the depth of your model here. And in this mode, we can also define the uh, groundwater head by entering the groundwater. Now, uh, next we have a structure mode. So in structure mode, to simulate the tunnel, first we have to click on the create tunnel button from the side toolbar. Now the tunnel designer window will appear. So now we have two different submodes, that is cross section submode and properties submode. So now in the cross section submode, we can have the we can define the shape, and we can either define the whole or a half tunnel. So since we are dealing with the circular, so we have chosen the circular tunnel here, and we are defining the whole tunnel. Now in because our tunnel is a circular section cross section, so we need to define the radius of the tunnel. And in subsection mode, we can define the thickness of our tunnel lining. Once that's done, in the properties mode, we can assign the properties of the lining by assigning it as a by creating a first edge as a plate, and then applying a plate property. So and to simulate the interaction between soil and tunnel lining, we can use the create negative interface. And for volume loss between the excavated surface and installed lining, uh, again we can use the contraction. We can create the contraction here, and then we can generate our tunnels. So here we can see that the tunnel designer in 2D is pretty simple here, because we are only dealing with the cross section of the tunnel. We only need to define the tunnel lining, and also if there is a volume loss due to excavation and installation of the tunnel lining, we can define that also as by using the uh, by creating the contraction. Now now next we have a, tunnel configuration. So by using the tunnel designer, we can create we can simulate different tunnel configuration. So the first figure is showing you the parallel twin tunnel with the horizontal alignment, and the second is the stacked parallel twin tunnel. Third is the tunnel with the inclined alignment, or where we have a diagonal tunnels. And the fourth one is a double O tube multi-phase tunnel, which was mainly developed in Japan for the urban environment. So using the tunnel designer, we can create uh, different tunnel configuration as well. Next, again, now we'll see how we can use the tunnel designer in 3D. So here again, we have uh, a simple case of a tunnel of 6 meter diameter, and a cover of two times the diameter. So before that, I'll explain you Now here, compared to what we have seen in Tunnel Designer in 2D, here we have two additional submode, that is trajectory submode and sequencing submode. So tunnel is inherently a 3D problem. So it involves various processes such as excavation cycles and application of phase pressure and grouting of gap between the lining and the tunnel wall, and installation of tunnel lining. So the tunnel designer in 3D have four sub modes. So the first one is the cross section sub mode. Here you define the your cross section of your tunnel or shape of your tunnel. So either you can have a circular cross section, and in case of you are going for in case you have a natum method, tunneling method, you can choose a free type of a shape, and you can define your shape of the tunnel. The second submode is the properties submode. Here you define the properties of the tunnel lining, the TBM conicity, the grout pressure, the phase pressure, and the check pressure. Now, the third mode is the trajectory mode, where you define the alignment or the trajectory of your tunnel, and you also define here the excavation your excavation steps or the length of your excavation step. And finally, in the sequencing mode, the tunnel boring process sequence is defined using the sequencing mode. Now, next we have a tunnel boring process sequence. Uh, the sequencing submode simplified the definition of the phases in the stage construction mode. So there are 8 repetitive steps in the tunnel boring process, and these steps define the sequencing of the tunnel boring process. And these 8 process also define which part of the TBM is active. So you can see here that we have three different parts here. The rear plane is will be corresponding to the your rear part of the your TBM. The front plane is corresponding to the front part, and the slice is the middle part or the shield, your shield of your TBM. So using the tunnel boring process, uh, we can easily define which part of our uh, TBM is active for a particular excavation. Next, we have a video uh, where I'll show you how to use a tunnel designer a 3D modeling. So here, similar to the tunnel designer 2D, we can create the tunnel using the create tunnel button, and then using the insertion point, we can define the location of tunnel in our soil model. Uh, After that, again, in the journal tab sheet, you can define the shape of your tunnel. Uh, and again, also you can define whether you want to create a full model or a half model. So in the segment tab sheet, we need to define the radius of the tunnel, and in subsection, we need to define the thickness of our tunnel lining. So you can also choose the orientation point, your starting point or orientation or point of your tunnel. So now, once the cross section of tunnel is defined, now we can proceed to the properties mode. Here again, you have to define for the modeling of the tunnel shield. You have to define you have to create the plate and then assign the plate properties. And for interaction between tunnel shield and soil, the negative interface can be created. Now, since the cross section of the tunnel boring machine is not constant. Usually, we have a large diameter of tunnel at the tunnel front, and the diameter decreases as we move towards the tail end. So to that, we can create the contraction, and for the contraction effect, uh, sorry, for the grout pressure, we need to define the surface load. uh, and we can also define the variation in the surface load from the top to the bottom of the as you're moving from the top of the tunnel face to the bottom. Now for face pressure, we can define the face pressure in the plain tab sheet, and by creating a surface load, uh, uh, we have defined our face pressure. And again, the variation in the phase pressure can also be defined uh, in the properties mode. So we have chosen the distribution as perpendicular and vertical increment. So our phase pressure is 90 kPa at the top, and and it increases with the 14 kilometer, sorry, 14 kilonewton per meter. Now, the next step is to create a tunnel alignment or a trajectory. And this Here the trajectory also defined the tunnel excavation path. So we can do that by adding the multiple tunnel excavation segments and path, and we can also define the each of our excavation steps. Now we have now moved to the next sub mode, that is sequencing. So here the sequence in sequencing, the sequence in which tunnel boring process is carried out by the TBM is defined. So each step of the TBM can be defined by adding a new step. So the first step of the tunnel boring process here is the to excavate the soil, and we can define that by deactivating the soil inside the uh, tunnel cross section, and then the phase pressure can be activated. Now next now the conicity or the outer shield of the tunnel will come into picture now, to define the conicity, uh, we have to define the difference in the diameter. So here we have used 0.5% as the tunnel conicity, and in each step we are starting from the 0%, and each step we are increasing the we are decreasing the TBM conicity. So up to step 5, we have a tunnel conicity, decreasing tunnel conicity of 5%. Okay, after that, uh, at the back of the TBM, the pressure due to the, sorry, this is the last phase, okay. And after that, we have a uniform conicity. Now, we'll add a new phase. And in this phase, at the back of the TBM, the pressure due to the grouting is modeled, as well as the hydraulic jack force to push the tunnel forward. So that was done by activating the surface load. And for hydraulic jack forces, we'll activate the surface load at the rear of the TBM, and we need to define what the value of the jack forces. What is the magnitude of the jack forces? Now, now the final stage or now final step is the installation of the final concrete lining. So for that, we have deactivated the grout pressure and again activated the negative interface. And we also have to activate the outer volume of the TBM. And in the plane rear sheet, we have deactivated our jack forces. So once that's done, now we can generate our tunnel. So these are the few of the simple step by using which you can easily simulate a tunnel or a tunnel boring process. And you know the tunnel designer is a very handy tool and a very and using which you can define your tunnel processes and model the tunnels. So next we have a different tunnel trajectories. Using the tunnel designer, you can have different tunnel trajectories, and your tunnel trajectory need not to be always a linear one. It could be a curved one, or it could be a descending type also. So here we have a few examples. So the first one is a descending tunnel, which is the practical case, and the second one is the loft going up tunnel, and the third one is the loft going down, and the final one is the sweep tunnel. So the trajectory option in the tunnel designer can also be used for can also be very helpful and effective tool when you want to define your curved tunnel trajectories. Now moving now next we have a tunnel face stability. So during the tunneling process, the tunnel face need support, uh, especially when you are dealing with very soft soil. And this support usually we provide this support usually in the form of liquid or air or ground pressure or a mechanical pressure. So and this support pressure must be between the maximum and the minimum value. And this maximum and minimum value depend on the your soil properties, your depth of the tunnel from the ground surface, and your groundwater pressure at the face of your tunnel. And if and a too low pressure at the tunnel face can lead to a inward collapse of the tunnel face, or which we can say active failure case. And if you will apply too high pressure, then that can lead to a blowout at the tunnel heading. So which will be the case of the passive failure. And because of this, because of either a very low pressure or either a very high pressure, this could lead to a large deformation at the ground surface. So in order to analyze the phase stability, so we have a model here. Now we have a chosen a tunnel of diameter 8.5 meter, and the length of the tunnel. Sorry, we have yeah sorry, and the length of the TBM is 8.6 meter, and the distance between the central axis of the tunnel and the ground surface is 9 meter. So it is important to not only find the factor of safety for your for a full length of your tunnel, but each and every step of the tunnel excavation is important, and need analysis or need a safety analysis in order to find the factor of the safety. So now Plaxis uses the C5 reduction method for the safety analysis. And in this method, the strength of the soil is reduced gradually until the failure is reached. And the factor of safety is the ratio of available soil strength by the to the strength at which the soil uh, of soil fails. So the C5 reduction method in Plexus C5 reduction method, the slip circle or the slip surface or the slip circle is the result of the finite element calculation. Unlike the limit equilibrium method, where we have to assume a slip circle for the analysis. So this here is the are the output of the tunnel phase stability. So the first figure is showing you the total deformation. The second figure is showing you the vector total deformation or movement of the soil, how the soil is moving. And third, you can see the affected zone of the inside the tunnel. And finally, you can see the slip circle in the incremental deviatrix strain. Now, uh, after the stability analysis, here we can see that when we have a phase pressure of 90 kPa, the factor of safety was 4.65, and this factor of safety decreased with a decrease in the uh, phase pressure. And when the phase pressure was 55 kPa, the factor of safety is 2.15. So, using factor of safety, you can find the minimum value at which your factor of safety is 1. So that would be your minimum value. So your phase pressure should be more than the that value in order to avoid a phase failure or a phase collapse. Now, moving to the second part of the presentation, here we have uh, a numerical simulation of a shield tunneling. Here, uh, we'll see how the stage construction in our stage construction part of the tunnel. So the stage construction window you can see on the left hand side of the figure of your screen. So and under the phase explorer, you can define the number of phases that will be corresponding to your tunnel advancement. And phase explorer has a default phase, that is the initial phase, and yeah, the initial phase involve the generation of initial stresses and geometry and configuration. And you can also have different calculation type depending on the type of problem you are dealing. So you can have a plastic analysis or a consolidation analysis, or for the safety. If you want to find if you want to find the factor of safety, you can go for the safety analysis. So next, for construction of the tunnel advancement. So the tunnel advancement in a stage construction can be defined by one of the three methods, or because a tunnel boring process consists of a number of excavation cycles, and the tunnel advancement can be done using one of the three method here. So first we have a manual method. So in this method, you add each of the phase manually, or you add each of the excavation step manually. Second, you can add the phases, or you can define your excavation phases by using the command line runner. And so for this, you have to have maybe a commands in a Excel sheet or a ASCII format, or also you can also have a macro. And the third one is you can also use a Python script for the tunnel advancement. And the Python script can be very effective method when you have a multiple excavation cycles, or when you are adding a very large, let's say 200 to 300 cycles. So now we have a short video in which you can see how we can use the all the three different tunnel advancement method. So here, the first one, you can add the phases manually, and in the model explorer, you can using the tunnel advancement, you can advance your tunnel excavation. But in case when you have a multiple cycles, this could be a very hectic process. So the second one, you can use the tunnel liner. So you have a here we have a tunnel Excel sheet, and in which we have the command for the current and next phase. So by copying the commands and by using the run option, you can run. And as you can see, the phase explorer, you have added 8 different phases now. So again, when you have a multiple cycles, when you have 200 excavation ring, so for that we have a tunnel advancement tool or a Python script. So by using a simple tunnel advancement tool, you can add multiple excavation cycles. So for that you have to define how many number of steps you want to add, and once the command process. So here again you can see you have added uh, 8 phases successfully. So using a tunnel advancement tool, uh, you can add multiple phases, and this could be very effective, and it can save you a lot of time. Uh, and this particular script file is available in Bentley community. You can download it from there. So next we'll see some what are the output that we can get from the after the analysis. What are the simple output or direct output we can get from the PLAXIS program. So now here we have a simple animation to show how the tunnel boring process using TBM is simulated. So the blue color rings are the TBM shield, and the gray ring is the your grouting, and the green one is your final tunnel lining. Uh, Next, we have examples of simple output that we can get directly from the PLAXIS. So the settlement and ground movement in tunnel is important, and it was observed that the typical shape of the transverse settlement is transverse settlement after the tunnel construction is similar to your Gaussian distribution curve, where we have a maximum displacement at the center of the tunnel. So the using the Gaussian distribution curve, this is very useful when you are doing a preliminary investigation, or you want to find the during the preliminary stages of your design, you want to find what's the maximum displacement you are getting. But by using, if you have a want to go for advanced analysis, you can use the finite element model, and using the finite element model, you can find the settlement or surface deformation or the surface settlement more accurately. Next, we have a settlement profile, which shows you the effect of the your phase pressure again, how the magnitude of the phase pressure is affecting your settlement at the surface. So when you have a very low phase pressure, you can see that the settlement or a surface settlement is increasing. Similar to phase pressure, grout pressure or magnitude of grout pressure also affect the surface settlement. So if the grout pressure is too low again, that can again uh, create a more that can result in a more surface settlement as compared to when you have a very high grout pressure. Next, here we have a total surface settlement during the shield tunneling. Here, the bottom figure, as you can see on the bottom figure, how we have a different as the tunnel boring machine progresses forward, how the settlement are increasing. So the A settlement is corresponding to the settlement by the phase, and B is corresponding to the that was caused by the overcut of your TBM cutter head, and C is settlement induced by your post by your shield or grout, this is usually a gap between your excavated surface and your shield. And D is due to the long-term settlement or due to the hardening of your grout. So as the tunnel moves forward, the settlement at the tail of the TBM machine increases. Next, we have the axial forces here. Uh, we can see that the bending moment in your tunnel liner. This also you can get directly as output from the when you are modeling your tunnel liner as a plate element. So the top and bottom of the bottom portion of the tunnel liner experiences the compressive force, whereas the side of the your tunnel liner experiences the tensile force. Now we can see few other examples. Compared to 3D model, PLAXIS 2D model is more fast, and it's simple, and it's very useful when you are mainly looking at the profile, looking at the cross section settlement or your axial force or your structural forces in your lining, tunnel lining. So here you can see we have our axial values, axial force values, and as well as the bending moment values. Now next, now uh, the final part of this is that now here are a few important key points or few challenges and solution when you are modeling a tunnel using a tunnel or tunneling process using a TBM, and when you are simulating it numerically. So the first challenge is to modeling of the TBM. Uh, the modeling of the TBM uh, 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 could be is a complex process because it involves different stages of the construction and various excavation cycles. By using the PLAXIS program smartly, you can model only those process which are important. You don't have to model all the process for all the process to get the correct results. So by using those correct modeling those process correctly, choosing a few excavation process, you can model the complex TBM problem easily. Now, second is the modeling of the lining. Now, in PLAXIS, the lining can be modeled as a continuum element or as a plate element. Now, plate element is simple and it will give you the structural forces directly. But now in a newer version of the Plaxis, you can also get the uh, structural forces in the continuum or a volume element by using the central line approach. So depending on your expertise and depending on your computational time, computational time or resources, computational resources you have, you can either choose a continuum or a plate element. And next, because the repetitive sequence of tunnel construction for the tunnel advancement, uh, when you want to add many phases or many excavation cycle, the tunnel advancement tool can be very handy and very effective. It can save you a lot of time and also a lot of effort also. And the final part is for the modeling of tunnel process, where you are dealing with uh, modeling of lining or grout pressure or face pressure or TBM conicity. So tunnel designer, using tunnel designer, you can easily model those steps or uh, those process of the tunnel boring using TBM. Now next, so for the those who are interested in interoperability between Plaxis and other structural software or Bentley system, we have a tool here, which is the integrated structural modeling or ISM. So the ISM allows you to share the structural engineering information among modeling, analysis, design, drafting, and detailing software. So using the ISM and structural synchronizer, you can easily share the structural information with other software. So the ISM process involves creating a repository of common data, which is known as the ISM repository, and this ISM repository is available in any ISM enabled product. And this ISM is free for the user of any structural program from Bentley. So using ISM, which is now available as a tech preview in Plexis 3D uh, in both update 2 and 3. So using ISM, we can import the structural model from any of the structural software of Bentley system to the Plexis. And those who are more interested can refer to the latest on-demand webinars on modeling of tunnel and tunneling, and also the last one, fourth one, that is interoperability in action for structural piping, geotechnical, and beam teams. So with this, I'll finish my presentation. Now, I think now if now we'll move to Q&A session. If you have any question, you can ask me. So over to you, Mr. Shiva.
Dr. William, do you want to speak anything?
Yeah, okay. All the presentations made here is connected with the latest release of PLAXIS. So Rajendra has demonstrated two sets of tools, the tunnel designer in 2D and 3D. So this is all connected to what we call right now the PLAXIS connected edition or CE edition. So as a C edition, you don't need the dongle. So it's in a way with this CE version, it's what we call a cloud-based type of a platform here. But any case, if there's nothing, I would like to close. Please, if you have any questions, you can forward this to Ramcats or to Dr. Rajendra Bisht. In the meantime, you can look at additional information at the our website here. For those of you who are using the Connect editions, you already have a Connect account. You can head to the Connect Center, where the links to the on-demand and live webinars and documents and the Learn servers are all there. Yeah. So with this, I thank you.
Okay. Thank you, Dr. William, and thank you, Dr. Ravindra Bisht. So actually,
Yeah, thank you everyone. Yeah,
yes,
thank you, Mr. Shiva.